The next tab we do is exposure, and this is where we've got some data on regional salt buildup levels and also on monthly temperatures for different parts of North America. And you can find your area, but based on a location, it pulls out of a database a level of a maximum surface concentration of chlorides through salt loading, essentially, and then the amount of time it takes for that it to reach that maximum level. And then this is then really your external exposure to chlorides. So by choosing a different place, let's see if we can do District of Columbia, Washington. There's this Washington, D.C. So in that case, it's pulled from the database a maximum surface concentration of 0.8% weight of concrete, and it's taking 13.3 years to reach that maximum. And then over here you can pick your particular type of structure. And for right now we'll pick parking garages in Washington, D.C., which are likely to have lots of cars in them today. And then the monthly temperature, the diffusivity of concrete varies with variations in temperature. So the higher the temperature level, the easier it is for chlorides to diffuse through the concrete. Based on these locations, you can pick values. If you have values of your own and want to modify them, all you need to do is uncheck this Use Defaults button, and now you can modify these values. If you wanted to set this to 1.0, for example, it's now modified that, and you can use those. And you can modify the maximum number of years. You can also modify the temperatures. The temperatures here, because we're in US units now, are expressed in Fahrenheit. If we switched over to SI units as our default, these would be in Celsius. To the point of this methodology, if in fact you have better information for, say, the state of Pennsylvania, just as an example, you could put those in here, modify the maximum levels and modify the number of years. If you use a lot of salt, you could go to 1.0 and a couple of years here. And you'll see those differences even for things like, well, right here we're in Washington, D.C., so it's not exposed to the ocean. But when you get to things that are close to the ocean, fairly quickly you're getting to high levels of chloride exposure simply because of direct splash or because of chlorides that are in the air. Okay, once we finish the exposure, then we go directly to making our concrete mixtures and our corrosion protection strategies. These are controls up here. We'll get to those. Here's a list of the mixtures and the important properties about them, the ones that are important to service life. So for each one of these mixtures, it'll tell you whether or not you've specifically made your own, not your own mixture, but your own set of concrete conditions, and I'll get to that. Here's the D28 in US units. Here's that M factor. Here's the level of chlorides necessary to initiate corrosion based on your mixture. Here's the initiation period, the propagation period, and then the sum of those two is the service life. So for each one of these, for example with M, if you hover over M, if you look on the left-hand side over here, when you hover over M, it gives you an explanation of what M is, the diffusion decay index, used to estimate the change in diffusion coefficient over time for basic concrete mixes as well as those that contain fly ash and slag. So what it's saying is if you add fly ash and slag, you will increase the M, thereby increasing the speed with which the concrete becomes denser. So for each of these mixture, if you click on one, it then shows you the values for that mixture. Here's our base case, and here's the description of what that is. And here are what its current properties are. It has a water cementitious material ratio of 0.42, and you can range to see how it shows you what the allowable ranges of values are for WCM. Those are the ones that the methodology allows you to input. You can put between 0.25 and 0.6 for WCM. Here's slag, has an allowable range of values of 0 to 70%. Fly ash, 0 to 50%. Silica fume, 0 to 15%. So for the base case, we're going to leave it untouched. We'll just leave it at these values. We're going to keep it with black steel, no inhibitor, and no barriers. Now let's look at alternative 1. For alternative 1, let's go ahead and add some silica fume, which is going to increase the initial diffusivity of the concrete. Let's add some inhibitor, which is going to increase the level of chlorides necessary to initiate corrosion. And then let's go ahead and add a little bit of slag as well. These are just arbitrary values, but I want you to be able to see the effect they have. By adding slag, we're going to speed up the rate at which the concrete becomes denser. Now, so we've changed these values and we've added an inhibitor. And now here at the bottom, you can see a comparison of the service lives. Base case has a service life of about 14 years. That number is the same as the number shown over here. Alternative 1 has a service life of 67.6 years, shown here as well. And this gives you some information about how Alternative 1 is different than the base case. So Alternative 1 here has a higher, a lower diffusion coefficient at D28. It has a higher value of M, which means that the diffusion coefficient is going to go down faster over time than the base case. It also has a higher level necessary to initiate corrosion, this 0.15 by percent weight of concrete, than the base case. And then what this results in is a longer initiation period for Alternative 1. It has an initiation period of almost 62 years. Add to that the propagation period, which is invariant, and you get the 67 years.